Hello everybody, this is Dr. Christopher White, and today we are going to be doing lecture number 5 where we're going to be looking at plate tectonics. So today I'm going to get the code word out of the way very early. The code word for this particular lecture is yellow, as in the colour. Alright, so here we go. So the idea of plate tectonics was initially put forward in 1912 by a gentleman called Alfred Wegener. And he proposed the model, essentially the basis, and showed the evidence for continental drift. So essentially his proposal was that the continents were moving through the ocean like battleships, essentially, ploughing through the seas. So of course, like any great scientific idea, it was instantly rejected by the majority of the scientific community. So his model helped to explain previous observations, but it didn't explain the mechanism, and that's one of the problems with the proposal, the hypothesis that he put forward. Essentially, he showed all this evidence to say, okay, I think the continents were once joined together and then moved away from each other, but at no point did he have the evidence to actually say why. Excuse me. So what was Wegener's evidence? So he presented 5 pieces to back up his... Now, I've written a theory up there. That should actually be the word hypothesis. My mistake. So the first piece of evidence he used was the jigsaw fit. The second piece of evidence is the tectonic fit. The third piece of evidence is the stratigraphic fit. The fourth is the glacial fit. The fifth is fossil evidence, and the sixth is Cratonic fit. Now, the Cratonic fit's slightly separated down there because Wegener didn't actually use this piece of evidence. This is a piece of evidence that's come to light more recently in the past 3 decades or so. So it should be pointed out that he didn't make all these observations. So in a lot of cases, he was actually using other people's data. And that's another point of attack because, you know, when you start using other people's data, can you really be certain that the data you're using is good? And that's especially true when you consider that he was using data from the southern continent, so South America, Africa, India, Australia, and Antarctica. And at around 1912, so the early 20th century, I've got to be honest, in terms of geology, we didn't have a particularly good understanding of those continents. So, he was using evidence, geological evidence, from those continents, and the vast majority of geologists didn't know much about the geology of those areas, and so people felt a bit, uncomfortable trusting his word. So, let's look at the piece of evidence. So the first piece of evidence is what's referred to as the jigsaw or the continental fit. So most of us as children probably noticed just how well the east coast of South America and the west coast of Africa would slot together if you were to push them towards each other. So if you take all the continents, especially the southern continents, so once again South America, Africa, India, Australia, Madagascar and Antarctica, and you move them towards each other and you try and stick them together using their continents, you actually get a pretty good fit. They'll form a landmass. Now the problem is that fit that you get is good, but it's not great. And the reason for that is that coastlines are dynamic systems. So a coastline doesn't remain exactly the same shape over very long periods of time. Some portions of it will undergo erosion, some portions of it will undergo deposition, and therefore will become larger, and of course the sea level goes up and down, so the coastline is constantly changing position. And so this means trying to match the continents up using their coasts is on the whole relatively successful. However, it's not a particularly great fit. So instead what you need is some kind of margin that's more resistant to change. So what's that margin? Well, it just so happens that, down here you can see we have a picture of the eastern seaboard, and you can see here is the continental shelf in the lighter blue, here is the deep marine abyssal plain here in the darker blue, and then along the edge here we have this, what's referred to as the shelf break, and that marks the edge of the continental shelf before the seafloor drops off very steeply towards the abyssal plain. So essentially it goes continental shelf here, shelf break, which is this red line. Then as you go over the shelf break, the seafloor drops off very fast, so it's a very steep drop. That's the continental slope. And then you end up down here on the deep seafloor, also referred to as the abyssal plain. So the shelf break here and the continental slope essentially are approximately between about 200 and 2,000 meters below sea level, and essentially it's the perfect margin. It's an area that doesn't undergo erosion. The amount of sediment deposited on it is relatively small, and as such, it hasn't really changed its shape much for a very, very long period of time. So if we lock the continents together using the continental slope and the shelf break, well, what happens? We end up with this diagram over here. And as you can quite clearly see, if we use the shelf breaks and the continental slope, then all of a sudden we can actually lock the continents together with extremely good accuracy. We get a very nice match. Now, this data wasn't actually available to Wegener and didn't become really available until after World War II. So that's why he didn't actually have this really great data to lock the continents together. He just had to use coastlines. I mean, you can actually see on this diagram here, if you just use the coastlines, the fit is good, but it's not really great. However, as soon as you use the the shelf break and the continental slope, everything locks together really quite nicely. So the second piece of evidence is the Cratonic fit. So cratons, or cratons, depending on how you want to pronounce it, are regions of extremely old crust that form the cores of the continents. And so the rest of the material that forms the continents essentially sticks onto the side of these very, very old pieces of crust. So mapping and dating of the rocks within these cratons indicate that several of them have remarkably similar stratigraphic sequences. They have the same sequences of rocks, and those sequences of rocks have suffered similar tectonic and volcanic events. So just to be clear, cratons or cratons date between 2 and 3.6 billion years old is the average age of the rock that's exposed. So they aren't going to record just one supercontinent. They'll typically record several supercontinent events. But what do we actually see? Okay, so here we go. So this is obviously the Earth, and you can see the cratons are marked out here. Okay, so that's the craton for North America. Obviously, you've got one in Greenland, Scotland, Western Europe. That's called Baltica. Then we have the Siberian craton over here. Now that's completely covered by younger sediment, so it's not really exposed. We have the China craton. We have the Northern Australian craton, the Southern Australian craton, the Western Australian craton. We have the West African, the Congo. There's a few other ones. Excuse me, like the Kalahari. And then we have Amazonia down here, and we have the Rio de la Plata down here as well. Okay, so these are very, very old pieces of crust onto which younger material has essentially accreted itself, so it's stuck onto the side. So what do we notice? Well, when we compare these rather disparate areas of crust, so let's say we compare, so let's look at this diagram over here. Let's say we compare something like the Congo to the San Francisco over here. So what do we see? Well, we see that, number one, these two areas have the same sequences of rocks, and we see they've been deformed in the same way. So when a geologist goes to an outcrop of rocks and they take measurements, we look at the angle and the direction in which the deformation occurred. And so what we can do as geologists, we can say, right, well, this rock over here was essentially deformed from, let's say, a northerly direction, and it produced structures that had a certain angle. And this deformation occurred at a certain time, which we can measure using radiometric dating. Then over here we have San Francisco. We can all do the same thing. We can take look at the rocks there. We can say these rocks were also deformed from a northerly direction. It produced structures with the same angle, and that deformation occurred at the same time. Now, when you look at, if they're in their modern position, look at the huge distance in between them. That would be very difficult to achieve if the continents were in their current position. The logical explanation is that these two areas of very, very old crust were once in near or direct contact with one another, and that would allow them to be deformed in the same way at the same time. And so when we do this, we can begin to see these cratons or cratons actually have you can see the links in between them. So the North American craton here is linked to the craton that makes up Greenland, and it's also also linked to the Cratonic material that makes up Scotland. Down here, we can see that the South Australian craton links to Australia. We can see that the Madagascan craton links to India. Okay, there's also some suggestion that this portion of the Antarctic and the Antarctic craton down here actually links to India as well. Baltica might link to Scotland, and there's, all obviously, as we can see here, these cratons that make up the west coast of Africa and the east coast of South America also have very, very strong relationships. So when we look at these cratons, we can see that there's a very good chance at some point, or several times actually, they were in direct contact with one another. And so once again, the reason for us believing that is if they were in their current position, it's highly unlikely that these areas could have the same deformation history. So it's highly unlikely that Scotland over here could have the same deformation history as these areas over here in central Canada. It's just not going to happen. So then we have the stratigraphic sequences. So if we map rocks on the southern continents, so that's South America, Africa, India, Australia and Antarctica, and we look at rocks between 420 million years ago, that's the lower Devonian, and 200 million years ago, that's the upper Triassic, we see that these sequences of rocks have a very strong set of similarities to them. And these connections are particularly strong between the upper Carboniferous and the lower Triassic. So what we need to remember is that these continents in their current position have a very wide variety of climatic conditions. So it's highly unlikely that similar sediments would have been deposited at the same time if the continents were in their present locations. So just remember, the types of sedimentary rocks that form in an area are a direct reflection of the environment in which the sediment is being deposited. So you have to bear in mind, does India have the same environment as Antarctica? The answer is no, and so you would expect to get different rocks being deposited if the continents were in their current position. Okay, so what are the two possible explanations for the sequence of rocks that we see here? Well, let's look at the sequences of rocks and actually, discuss what we see to start with. Okay, so at the bottom here we have the basement. That's the stuff the rocks have been deposited on. That's very, very old rock, and we're not going to worry about that. So directly above the basement in the Carboniferous here, we have a sequence of this kind of very, very tan-coloured rock here, and those are glacial deposits. So in the Carboniferous, we can see that each of these 5 continents here have a sequence of glacial deposits being, covering the area. On top of that, we then have a sequence of coal beds. So coal beds are deposited in warm, humid climates. So think, the Everglades, the Okefenokee in Georgia, Louisiana, somewhere like that. So very warm, very humid climate. So we've gone from a very, very cold climate, which will produce the glacial deposits, to a kind of warm, humid climate, which will produce the coal deposits. Then on top of the coal deposits, we have a sequence of sandstones, and those sandstones are of a desert origin. So essentially we've gone from glacial deposits, so cold, to essentially the kind of environment where you can form coal, that's going to be warm and humid, to sandstones, warm and dry. So each of these areas show remarkably similar sequence of rocks. Now, think about this for a second. Obviously, Antarctica, that's absolutely fine. We can explain, why Antarctica would have glacial deposits in its current position because, let's face it, it's over the South Pole, it's cold. That makes perfect sense. But South America, Africa, India and Australia aren't exactly cold continents. So the idea of being able to cover those in very, very large glaciers is actually pretty unlikely if they're in their current position. So then the same goes for the coal formations. Coal formations, as I say, require warm, humid environments. So that would require, obviously, Antarctica to be a lot warmer and a lot more humid than it is now if you want to form coal deposits. That's pretty difficult to do if it was in its current position. And then we have the sandstones. Once again, very difficult to form sandstones in the cold environment of Antarctica. Same for India. India's environment tends to trend towards relatively warm and relatively wet, so you don't really get many desert deposits being formed in India. Now, in the case of Australia, South America, and Africa, you can maybe get some desert deposits forming there. So, if the continents are in their current position, it's very difficult to explain how these continents have the same sequence of rocks. And essentially, if you were to do it based on environment, you would have to come up with a mechanism that would allow you to homogenize the entire environment across the southern hemisphere. If the continents are in their current position, and that would be extremely difficult to do. You can't really homogenize an area that big. It's very tricky to do that. So it's a highly questionable idea whether you can do that. So then you have to think to yourself, well, is there any other way that these rocks could have the same geologic history? And the answer is, well, yes, if they were joined together and moving as one landmass. So if we take South America, Africa, India, Australia and Antarctica and we join them all together, we form the landmass Gondwana. So then when we look at the rocks, we can say, well, where was Gondwana likely to have been? Well, actually, when you think about it, it begins to make perfect sense. So let's take a second. So if we think about these glacial deposits, that would suggest that Gondwana is going to have to be located somewhere around the South Pole in order to form very, very large ice sheets. Kind of makes sense, doesn't it? Now, then we have these coal deposits, and that suggests all of a sudden Gondwana is in a relatively warm, relatively humid environment. And that would suggest that it goes from this South Pole environment and it begins to migrate towards the equator, and as it approaches the equator, the climate becomes much warmer and a lot more humid, and then all of a sudden you have the correct environment for beginning to form these coal beds. Now, in terms of the sandstone, that would suggest that it's got into an area either slightly above or slightly below the what are they called? The tropics of Cancer and Capricorn. Okay, so that would suggest, either Gondwana ended up somewhere in this kind of region around where the modern Sahara is, or down here around where the modern Namib or Australian deserts are, somewhere in that area where the climate tends to be rather dry and rather warm. So it would suggest that essentially, if we assume these continents are all joined together and moving as one landmass called Gondwana, it started off over here by the South Pole, migrated towards the equator, and then either kept going north or came back south a little bit. And so all of a sudden, by joining the continents together, we can come up with a relatively reasonable explanation as to why they show the same geologic history. So the next piece of evidence is the tectonic fit. So when two pieces of crust slam into each other, essentially it will produce a lot of deformation. Just like two very, very large cars crashing into each other head on, the engine blocks will essentially crumple and deform. So, the classic example of that is something like the Himalayas or the Alps or the Andes. That's essentially where the crust is deforming in response to two pieces of continental crust, or in response to two plates banging into each other. So, analysis of lithologies and deformation have revealed that several disparate ancient mountain regions have suffered the same deformation events. So it's just like the Cratonic fit, but with slightly younger rocks. So a good example is if we look at, let's say, the Appalachian Mountains. And if we look at the Appalachian Mountains, we can see once again the rocks have been deformed from a certain direction at a certain time, and it's produced a number of structures that have the same have a fixed orientation to them. So then we go over to areas like the Atlas Mountains in Morocco, in northwestern Africa, and we look at rocks there of the same date, and we see that they have also been deformed in the same way. So they've been deformed from the same direction to the same intensity at the same time, and it's produced similar structures with a similar orientation. Now, once again, if the continents are in their current position, that's very difficult to achieve. So you would have to come up with a process that would allow you to produce all these structures at the same time, the same intensity, being deformed from the same direction on two very, very distant continents. As soon as you say, well, maybe the continents would join together and this deformation was the result of them banging into each other, producing a mountain range, as soon as you say that, all of a sudden it makes sense very, very quickly. So these areas where we see these similarities in these ancient mountainous regions would be fine if the region is next to each other, but they're often spread across areas. So in the case of the Caledonian orogeny, the Caledonian mountain building event, we see that event occurring in North America, Greenland, Norway, the United Kingdom, Germany, and Poland. So, it was quite a big mountain building event, and, you would have to come up with a mechanism that would allow you to deform the rocks in the same way, at the same time, over a very, very large area if the continents were in their current position. But if you say, no, the continents were actually joined together, so these areas were actually right next door to each other, then all of a sudden, as soon as you do that, it begins to make a lot more sense. So this kind of gives you some idea here. So this is actually the Caledonian orogeny. Okay, so this is Laurentius, that's ancient North America. We have Baltica, that's Western Europe, and we have Avalonia, which is a little microcontinent that includes areas of the eastern seaboard, the United Kingdom, and a little bit of northern Germany. So what do we actually see? Well, we see there's a chain of mountains that comes all the way down here along the east coast of Greenland and then sweeps down the east coast of the United States, and we see another chain of mountains that sweeps down here through Germany and Poland. And so what's happened is Baltica's crashed into Laurentia, and then Avalonia's crashed into Laurentia and Baltica. And that's produced essentially a set of mountains that are, were produced by the collision. And when we look at the rocks on this side, so see the east coast of Greenland, and we look at the rocks over here in Norway, we see they've suffered the same deformation history. Now, if they're in their current position, you would have to explain that, taking into account the huge distances in between them. But if you say, no, they suffer the same deformation history because they once crashed into each other, then all of a sudden the explanation is rather straightforward. So this is a lot like the jigsaw fit we get with the continents, but essentially we use these ancient mountain ranges and the dates at which deformation occurred to allow us to link these land masses together. Okay, so it's been 20 minutes, so if you want to take a minute, stop the presentation, get up, have a walk around, get a glass of water, and come back to me in a couple of minutes, please. Okay, everybody. So, now we're going to think about the next piece of evidence, which is glacial evidence. So, as previously discussed, we get these glacial deposits in the bottom of the stratigraphic sequence in the Carboniferous. So here we go, glacial deposit, there, and there. So in the Carboniferous, we have these glacial deposits across all these 5 southern continents. So we already know that occurs. Now, what we do next is we look at the ice directions. So we say, how was the ice moving across these regions at that time? So what we realise is that if we look at the ice directions, it looks like they are radiating from a central point. Okay, so here's the diagram here. So, so this is the area that we believe was covered by ice in the Carboniferous, and these are the ice directions marked in red arrows. So we can see, in terms of modern position, it was northwest for South America, north for Africa, north for India, north for Australia. Okay. Now, if we just jump back to this diagram over here and we assume that the continents are in their current position, you could actually say that makes sense. Imagine you have an ice sheet coming from Antarctica. It starts moving north. Well, what's going to happen? The ice is going to move approximately northwest across South America, north up Africa, north up India, and north across Australia. So if the continent's in their current position and you form a giant ice sheet, it starts to nucleate from Antarctica, and it starts to move across these southern oceans and in a northerly direction, then all of a sudden the ice directions make sense. So you can argue that these ice directions don't actually mean that the continents were in direct contact with one another. There is, however, a problem with that argument. So if you have ever seen a map, you will know that Antarctica is white because it's covered in ice and snow. However, as soon as you get to the coastline of Antarctica, what happens to all that ice and snow? Well, it doesn't go much further. It will go a couple of kilometers past the coastline into the oceans, but it can't really go that much further. So the question is why is that? Well, even though ice is less dense than water, it's still, a pretty significant layer of ice that's going out into the oceans. And so when the ice goes out into the oceans, it comes off the ground of the continental crust that can support it, and it goes into the oceans, and the oceans can't really support it that well. So the layer begins to sag. And as the layer begins to sag, it begins to stress, and eventually it gets so stressed that it will begin to break. So think of bending a plastic ruler. You can bend it, so it will flex for a long time, and then eventually you get to the point where the plastic ruler snaps. Okay, and once that happens, the ice sheets that are entering the water break up into big chunks of ice that we refer to as icebergs. So very, very large sheets of ice, like sheets of ice that come off Antarctica, can make it a couple of miles off the coastline, at which point the ice sheets begin to fall to pieces. So the idea of being able to cover the entire southern hemisphere in a sheet of ice is actually very, very unlikely. So as soon as you discount that option, you need to come up with a better way of, better way of explaining these glacial sequences that we see. And once again, as soon as you say, all right, the continents were joined together, and we use these ice directions to show us where was the ice coming from, and it looks like it was coming from somewhere around here, started nucleating around here at the southern African Antarctica boundary. We say the ice starts to form around here, and it spreads out northwards that way, northwestwards that way, especially what is now in northerly direction in India, and this way for Australia. And thereby, as soon as we do that, we begin to see that all of these deposits make sense, and we begin to see that the ice must have started to form somewhere around here. And so we know that this area around here was very likely to have been the approximate position of the ancient South Pole during the Carboniferous. Now, in terms of the striations themselves, when we look at glacial rocks, we see two things. The first thing is what we're talking about here are not valley glaciers. So valley glaciers are the ones you get in mountains. Now, they form wherever you have very, very high topography that results in very, very low temperatures. So mountain ranges are very, very tall, and so they're very, very cold. Now, these glaciers we're talking about are what we refer to as continental glaciers. So these are really, really big ice sheets that push across the land and don't take any real notice of topography. They'll plough through hills, they'll plough through forests, and as they're ploughing along, they will strip off the topsoil as they go, exposing the bedrock underneath. So these ice sheets move straight over the bedrock. Now, at the bottom of these ice sheets, there's lots of very, very fine particles of material, lots of sand-sized bits of rock, lots of silt-sized bits of rock. And these sand-sized and silt-sized bits of rock are dragged along by the ice, and so they drag across the exposed bedrock underneath the ice. And so these very, very small pieces of rock end up polishing the ice, and so it produces what's referred to as a glacially polished rock. So the rock becomes very, very smooth. In fact, it becomes so smooth in some cases that it's like walking on ice. It's actually quite dangerous. So what else is in the bottom of the ice are not our larger class, cobbles and gravel and boulder-sized class. Now, when these are pulled along the bedrock, they don't polish it. They leave these gouges as they go, and they're referred to as the glacial striations. And they tell you the direction in which the ice is travelling. So if we look at these glacial striations here, we can quite clearly see that the ice is moving in this direction, that direction, this direction, and at some point the ice has clearly also been moving in this direction, but there's no arrow for it. Okay, so this is how we know the direction in which the ice was moving. We can look at these glacial striations, we can come up with a general trend. So in the case of this picture, the general trend is the ice was moving approximately east to east-northeast in direction on the whole. Now, how do we actually know which direction is right? Was the ice travelling this way, or was the ice travelling this way? And it's actually a very, very simple way of working that out. All you have to do is stroke the striation. So if you stroke the striation in one direction, the direction of travel, this way, it will feel smooth. If you stroke it in the opposite direction, against travel, it will feel rough. And that's it. So if you're ever in one of the northern states or in Canada and you see a load of people laying face down on a rock, stroking it, that's what they're doing. They're trying to work out which way the ice was moving that once covered that rock. So the final piece of evidence is fossil evidence. So what we realised, as human beings began to push out across the globe, especially in the southern continents, is that we get the same fossilised plants and animals occurring across some or all of the 5 Gondwanan continents. So remember, Gondwana is South America, Africa, India, Australia, and Antarctica. So when you consider the distance between these continents, if they're in their modern position, and the differences in the climate that they have, that's a bit strange. How can you have the same plants and animals occurring in India that you also get in Antarctica? Doesn't really work, does it? So we have a bit of a problem there. So this is what we see. So, there are 4 organisms in particular that show this quite nicely. The first one is Glossopteris. So Glossopteris is a type of what's referred to as a gymnosperm. It's a type of plant that includes the ferns. And it was a tree-like plant that grew to a height of approximately 40 meters, and it liked relatively warm, slightly moist conditions. So kind of temperate environment. So think of, the kind of environment that a modern oak tree would like. So what do we see of Glossopteris? Well, we see Glossopteris occurring in South America, Africa, Madagascar, India, Antarctica, and Australia. Now, in modern times, that's a pretty broad range of climates. You go from the freezing conditions of Antarctica to the dry, warm conditions of Australia to the warm, wet conditions of India. So that's a pretty significant difference. So the probability of you being able to have the same plant that can survive on these three continents, for instance, is relatively low if they're in their current positions. So that's a problem. So then we have organisms like Sarganthus, that occurs in both South America and Africa. We have Lystrosaurus. So Lystrosaurus is actually a type of very, very large amphibian. It's not actually a dinosaur or a reptile. It's actually part of the family that includes frogs. And so Lystrosaurus occurs in Africa, India, and Antarctica. Well, you can quite clearly see the problem there. I mean, okay, Lystrosaurus could probably survive in Africa and India, that would be okay, but the probability of a very, very large amphibian being able to survive in Antarctica if it's in its current position, well, that's pretty unlikely. And then we have Mesosaurus down here. Mesosaurus was a freshwater marine reptile, or should I say semi-aquatic reptile. And we find that once again in South America and Africa. So what do these fossils actually show us? Well, let's look at Glossopteris first. So here are the southern continents again that form Gondwana: South America, Africa, India, Madagascar, Australia, and Antarctica. So when we look at Glossopteris and we look at its distribution, what do we see? Well, we see that Glossopteris forms this nice circular band. So we actually get these kind of bands in the environment now. So think of the equator and think of the rainforests that form along the equator. That's a band. And that band essentially is a band where you have very, very similar climatic conditions, and so you get very similar organisms growing in those environments. You get rainforests along essentially around the equator. And so what this band is telling us is that these Glossopteris plants were essentially in a band that was of a similar climatic conditions at the same time. Now, once again, if the continents are in their current position, that band would actually be pretty difficult to achieve. So just think about it. Okay, you could say, well, maybe the band could go from southern South America into southern Africa and maybe across to Australia, including Madagascar. That might work. But India would be too far north and Antarctica would be too far south to really form a band that would work. So that doesn't make much sense. So the only way to explain this band is to say, okay, if all of these continents were together at the same time, then all of a sudden explaining this band becomes far more straightforward. So let's say the South Pole is somewhere around here, and then we have this climatic temperate band, a bit like, the northern states around here. This high latitudinal temperate band in which Glossopteris was surviving. And then all of a sudden, it makes sense quite quickly. So then we have Mesosaurus. So that's a freshwater reptile that occurs only in Permian age rocks from southern Brazil and South Africa. So here we go. So here's Mesosaurus there. So the first thing you're thinking is, right, marine reptile. It could have swum the South Atlantic. To which the answer is no. So you probably know that if you take organisms that like to live in fresh water and you put them in salt water, very bad things happen. So it's highly unlikely that Mesosaurus would have had the capacity to be able to swim from South America to Africa. So once again, we have to be able to think of another mechanism that would allow it to get onto both continents. So then we have Sarganthus and Lystrosaurus, and they're both land-dwelling reptiles. That's actually incorrect, as I said. Lystrosaurus is actually an amphibian. And in terms of Sarganthus, we see it in South America and Africa, and Lystrosaurus, that's Africa, India, and Antarctica. So what we're seeing here is the distribution strongly suggests that the continents were joined, and it would also suggest, based on Glossopteris, that these continents showed very, very similar climatic conditions. And that would allow organisms to move from one continent to another relatively easily because the continents were in direct contact with one another. So it's, rather easily explained. So how would we explain something like, let's say Sarganthus. So let's look back at the diagram here. Oh, going too far. Okay, so Cyanogaphus. So here we go, this animal here. Well, let's just say it starts off here in South America, if the continents are in their current position. In order to get to Africa, it's going to have to go on quite a long trek. So it starts in South America, it works its way through Central America, gets into North America. Okay, that's kind of okay, that's survivable, not many adaptations required, the climate is, changeable but relatively similar. Now, as soon as Cyanogaphus starts hitting northern Canada, Alaska, and the Bering Strait region, it's in trouble, because all of a sudden it's going from a warm to temperate climate into a very, very cold climate. So Cyanogaphus would not be able to survive in those conditions normally. So obviously it would have to evolve. It would have to develop the capacity to make its way through those cold areas. So eventually it does that. It makes its way across the Bering Strait. Now it's in Northern Asia. So it comes out of the cold regions of Northern Asia, it goes straight into the Central Asian deserts. So now it's got to change. It's got to go from being able to live in these very, very cold conditions to being able to live in these very, very hot, dry conditions. Once again, evolution would have to kick in. So then it covers this, let's say it makes its way through the Central Asian deserts. Well, obviously then the next thing it's going to hit is the Himalayas. Hits the Himalayas, well, once again, it's got to evolve, hasn't it? So it's got to be able to evolve the capacity to move through mountainous areas. So, it's got to evolve the adaptations required to move through that kind of terrain. Then it comes down the other side of the Himalayas, and now it's moving into the drier areas of the Middle East. So once again, it's got to change again, it's got to evolve, and then finally from the Middle East into North Africa, and then finally down into Central and Southern Africa. So what is pretty clear is that in order to make it from South America to Africa, it obviously has a very extensive journey, and the only way it can achieve that journey is through repeated evolutionary steps. So the problem then becomes you have to ask the question is, the organism that leaves South America, by the time it makes it to Africa, is it the same organism? And the answer would be a resounding no, because obviously it would have undergone so many evolutionary steps in between, it would be a completely different animal. So what we have to bear in mind is this idea of organisms being able to walk from South America to Africa, taking the if they're in the continents or in their current position, it just doesn't work. The most logical explanation is to say the two continents were once joined together and the organisms could simply walk from one to the other without any serious effort being required. So once people began to realize that these fossils showed these links, and excuse me, I'm going to yawn. Sorry. So once people began to realize that these fossils show these links and that it was suggesting the continents joined together, people who didn't believe that idea had to come up with an explanation for it. And the explanation they came up to explain this distribution of fossils were land bridges. So land bridges were used as a method to explain the fossil distribution seen across the 5 constituent Gondwana continents. So a land bridge is a connection between two land masses that allows plants and animals to migrate. And to be clear, they do exist. So that these aren't made up, they actually do occur. So for instance, land bridges can be the result of changes in sea level. So during the last ice age, the United Kingdom was joined to France because the sea level was so low that the English Channel, which is the body of water that separates the two countries, didn't exist. So animals could simply walk from France into the United Kingdom. You can also have land bridges formed by freezing. So every winter the Bering Strait freezes up, and in theory you can walk from Alaska into Russia. And then finally we have continental collisions. So the Isthmus of Panama, essentially, that's where South America makes contact with Central America, and once that occurs, essentially you have a land bridge, and that allows organisms to migrate from North and Central America down into South America and vice versa. So land bridges are not at all uncommon, so we know they definitely exist. So the problem is, if we are going to use land bridges to explain the same fossils occurring in Africa and South America, it's a real stretch. You would literally have to have a land bridge that would cover the entire South Atlantic. And if you were to have a structure like that, it would have to be pretty substantial. And so, as geologists, when we come along, we look at the seafloor and we look at the rocks, do we see any evidence for any kind of land bridge? The answer is a resounding no. we see absolutely zero evidence to suggest there was any kind of physical connection between South America and Africa, if they are in their current position. So there's no way an animal could have directly migrated from one to the other. And this explanation down here kind of shows you, what would happen if one of these organisms tried to migrate from Africa to South America or vice versa. But we've already discussed this, so I'm not going to worry about it. So let's see. So yeah, so once you get rid of land bridges and you say, well, these very long migrations just won't work, the only possible explanation for these fossils, for the same fossils occurring on different continents in rocks of the same age, is to say the continents were once joined together and the animals could simply migrate from one continent to the other with relatively little effort. Or it was aliens. That's the only other possibility. Alright, so we've been going for 20 minutes, so once again, time to pause the presentation, take a break, get up, have a walk around, get a glass of water, and then come back to me in 2 or 3 minutes. Okay, so that was the evidence that Wegener used to essentially back up his theory of plate tectonics. So, as I discussed, Wegener took the view that the continents were like battleships. So the one problem with his theory was this: obviously, for a battleship to get from point A to point B, it requires engines and propellers to actually move it through the water. So the problem is that Wegener at no point actually proposed the mechanism that would drive the continents through the oceans. So now we need to try and come up with, explanations to actually, number one, show the continents are moving, and number two, explain why they're moving. So the first stage of this occurred in 1962, and it was a gentleman called Henry Hess. He published a book called The History of Ocean Basins. Now, Henry Hess was in the US Navy in World War II, and he was based in the Pacific. And so it was his job to take measurements of the seafloor, and he noticed two main things. The first was that the oceans are shallower towards their centre along ridges that sit up to 1.5 kilometers above the seafloor. So the deep ocean is an area of the world that is extremely flat. It's almost billiard table flat. So, all of a sudden, when you come towards the middle of the oceans, like the middle of the Atlantic, for instance, you will all of a sudden hit an area of high ground. So you'll go from this very, very flat topography, and then all of a sudden the topography will rise up by about 1.5 kilometers on average. So that's a bit strange. And this area of raised topography on the seafloor doesn't form these isolated little mounds, it forms these long ridges that stretch over very, very long distances. So that's the first thing that he noticed. The second thing he noticed was that the deepest parts of the seafloor were along the continental margins. Now that's in the case of the Pacific. So if we go from the southern tip of South America, we can pretty much follow a trench that runs all the way from the southern tip of South America up the west coast of South America, west coast of Central America, west coast of North America, all the way across the east coast, so across the eastern seaboard of Russia, down towards Japan, down towards the Philippines, down towards New Zealand. We can essentially get a trench that goes nearly all the way around the circumference of the Pacific Ocean. And this trench is once again a linear feature, and in the case of the trench, the seafloor drops off very, very quickly. It can drop down in some cases, from about 4,000 to 6,000 meters water depth, all the way down to about 10 or 11,000 meters water depth. So, and that's pretty deep. Of course, one of these trenches gives us the deepest point on the surface of the Earth, which is the Marianas Trench. So, what Hess envisaged was that new crust was being made at these raised areas in the centre of the oceans. It was then moving laterally away from those raised areas, and then the old crust was being destroyed at the trenches along the edges of the continents. So, how did he explain these raised areas? Well, he explains these raised areas, these submarine ridges, by saying the mantle underneath them is clearly much hotter than the mantle, either side. So this means the mantle here is very, very hot, and so because it's hot, it's buoyant, and it naturally wants to rise. So think of the Earth's crust like a cotton bed sheet. So let's say there's 4 of us, and each of us grabs the corner of a cotton bed sheet and we hold it loosely. And then a 5th person comes along, and that 5th person has two or three helium balloons. And so they throw those helium balloons under the blanket. Well, what's going to happen? The cotton blanket is going to start doming up because the helium balloons are less dense than the air and they want to rise. And that's exactly the situation that Hess suggested was occurring underneath these submarine ridges. The mantle down here was a lot warmer than the mantle either side, and so it was therefore less dense. It naturally wanted to rise, and it caused the crust above it to begin to dome up, producing these ridges. Now, he said because the mantle underneath these ridges was a lot hotter, it was probably going to melt. Obviously, when it melted, it would produce magma, and that magma would lead to the formation of new seafloor. And that was his model, and it's a pretty logical model. Now, the problem is if you're creating new crust at these mid-ocean ridges, well, if you didn't get rid of old crust, then the surface of the Earth would just keep getting larger and larger and larger, and that doesn't work. So that means you have to get rid of old crust, and so then you have to look for, the question becomes, where is the old crust being destroyed? So when you think about it, well, the best and most logical place is, well, at the oceanic trenches. What he's saying is the new crust that's formed will move laterally over time until it comes to these oceanic trenches where the old oceanic crust dives down into the mantle, where obviously it's heated up and eventually melts. And that's his model. And it's a relatively logical model based on the evidence that he had at the time. Now, the problem is that the model he suggested once again has no driving mechanism. He has pretty good evidence to support what he's saying, and it makes a lot of logical sense, but there's no explanation as to what's actually causing this process. Okay, so in 1963, Frederick Vine and Drummond Matthews published a paper called Magnetic Anomalies over Oceanic Ridges. So what their paper did is it identified magnetic variations running parallel to mid-ocean ridges. So you're thinking, what? So what actually happened? Well, Frederick Vine and Drummond Matthews were British, and they were in the Royal Navy during World War II. And so they had to hunt for German submarines hiding in the North Atlantic. And one of the ways they did this was they used the Earth's magnetic field. They used what's called a magnetometer. And so a very, very large piece of steel or iron, like a submarine, will affect the Earth's magnetic field. So if you're on a ship going over where the submarine is and you have a magnetometer, you can detect these changes in the Earth's magnetic field caused by this big lump of steel. So that's one of the ways they try to detect submarines. Now, the problem was, and one of the interesting things they found out was as they went over the mid-Atlantic ridge in the middle of the Atlantic, all of a sudden, strange things began happening. They began seeing that they would start getting positive and negative magnetic signatures from the rocks on the seafloor. And once again, that caused a lot of confusion. So, where are we? Did I show the diagram? No, of course didn't. That would have been too easy. So they also saw that these magnetic variations were exactly the same on both sides of the mid-Atlantic ridge. So essentially, that would suggest that you're getting these changes in the Earth's magnetic field that are causing the magnetic signature of the rocks to be either positive or negative. And because new crust is constantly being made at the mid-Atlantic ridge here, and it's being pushed laterally, every time the Earth's magnetic field changes, essentially it means that the old crust gets pushed away and instead it will get studded. So we'll see the old crust moving away from the ridges, and we'll see this like barcode set of lines. Now, don't worry, I'm going to show you some slides later on that's going to explain it somewhat better. Now, then in 1963, I should point out, by the way, going back to Frederick Vine and Drummond Matthews, essentially what they're showing there is they are definitely showing that new crust is being made at the spreading ridges, and it's moving away laterally from the spreading ridges. That's what Vine and Drummond Matthews said. So that their evidence supports Henry Hess quite nicely. Okay, so then in 1963, a chap called Tuzo Wilson proposed what are referred to as hotspots to explain the presence of volcanoes away from likely magma sources. So, so this is the case in the North Pacific. So over here we have the Aleutian Islands, a very volcanically active chain of islands. And if we're saying that Henry Hess is correct, and the trench that runs along the front of the Aleutian Islands here is where the oceanic crust is subducting down into the mantle and melting, that's obviously going to produce magma. That magma will rise towards the surface where it can feed volcanoes, which are part of the Aleutian Islands. So, explaining the Aleutian Islands based on the Henry Hess model, it makes perfect sense. But then all of a sudden, you have Hawaii. Hawaii is nowhere near any kind of normal source of magma. So it's not near a trench, it's not near any kind of situation where you would expect very, very large volumes of magma to be being produced. So you have to come up with an explanation as to why it's there. So when you start thinking about it, you have to say, well, clearly there has to be some kind of very, very large magma source to feed the volcanoes. You have to remember the volcanoes on Hawaii are massive. So when we think about the Hawaiian volcanoes, we think about the part that's just above the ocean, just above sea level. You have to remember that the Hawaiian volcanoes, when they started forming on the seafloor, and they eventually made it above sea level. So the Hawaiian volcanoes aren't just, the couple of thousand meters we see now above sea level. They're actually somewhere in the region of 4,000 to 5,000 meters high. That's from the seafloor to their current maximum height now. So these things are huge. That requires a lot of magma. The other thing that we began to realize was that you don't just have one of these islands. This is the big island here of Hawaii there. There's actually a whole string of Hawaiian islands. Most of them are now underwater. You can't see them anymore, that run in a northwesterly direction. So once again, to form each one of these islands would require huge quantities of magma. Now, all of these islands here are extinct. The volcanoes on them no longer erupt, so they're inactive. It's only these islands here that are currently active. And so what Tuzo-Wilson said is, well, what would happen if there was a huge ball of magma that got stuck underneath the crust right here? And he called it a hotspot. And he said that this huge ball of magma essentially would make its way through the oceanic crust, eventually onto the seafloor, where it would start erupting, forming massive volcanoes that would eventually form islands. Now, it makes reasonable sense. Now, then what Tuzo-Wilson said is this. When we have chains of volcanic islands associated with subduction, these trenches, they form this very, very curved shape. They're called island arcs. These lines of volcanoes associated with hotspots are almost straight. They're what are referred to as linear ridges. So what Tuzo-Wilson suggested was the hotspot acted as a fixed location, and the plate, in this case the Pacific plate, was just rolling over the top. So that would mean that this island over here, for instance, okay, this one I'm pointing to right there, would initially have been over here. The volcano was erupting, went and formed this very tiny little island, and then slowly over time, as the plates moved towards the northwest, it has taken this island in a northwesterly direction, and then behind this island here, more islands have formed, as new crust rolls over the top of the hotspot, producing new volcanoes. So essentially, that means that Tuzo-Wilson has now provided evidence to show that the plates are moving. So he's saying in this case, you can see the Pacific plate at the moment is moving in a northwesterly direction. And then we have the Emperor Seamount chain up here. That's in approximately a north-south direction. So that would suggest that for a while, the Pacific plate was moving northwards, like so. And then eventually, I should say northwards like so. And then the direction of travel shifted to a northwesterly direction, and so the Emperor Seamount chain ended up over here. And so this gives us an idea of the direction of travel. So it shows us that the plates are definitely moving, and that the direction in which they're moving. And so once again, another piece of evidence to suggest that Hess is correct, but there's still no mechanism. Tuzo-Wilson is also important because he proposed transform or conservative plate margins. That's where obviously the plates move past one another without crust being made or destroyed. So that's, I know it sounds rather straightforward and rather obvious, but someone had to propose that idea, and that person was Tuzo-Wilson. So then what happened in 1966, a chap called Dan Mackenzie used his knowledge of radioactive decay, thermodynamics and continental drift, and also his knowledge of magnetic anomalies to produce a robust model for what was going on underground to actually drive the process. So what he realized was that the mantle, down by the core mantle boundary, was getting very, very hot. When it gets hot, it becomes less dense and it naturally wants to rise. And so that's exactly what it does. It starts to rise until it moves up towards essentially the base of the crust, at which point it starts cooling down. Which, as it begins to cool down, it becomes denser, and then it will begin to sink down back towards the core mantle boundary again. So essentially we have convection cells, just like the convection cells that form in a pan of boiling water. And because the mantle is convecting, that's essentially what's causing the plates to move. These convection cells are pulling the plates along with them. And there's a diagram coming next that hopefully will kind of show what I mean. Nope, there isn't. The diagram's going to be in a couple of slides' time. I do apologise. Okay, so we're just going to quickly jump back to those magnetic anomalies that Drummond and Vine found. So the Earth's outer core is made up of liquid nickel-iron alloy. So this nickel-iron alloy, as it circulates around in the outer core, it produces electric currents. So these electric currents interact with the Earth's natural, very, very weak magnetic field, and it produces what we refer to as a dynamo, or a dynamo effect, should I say, and that leads to the formation of a very, very strong magnetic field. So the magnetic field that we detect with things like compasses is actually this secondary magnetic field, this very, very strong one. So we can see that. So we can see magnetic fields in this environment here. So here we have a bar magnet, a table covered in iron filings, and when we put the magnet down, we'll obviously see that the iron filings form these distinct curved lines. They're called force lines. Okay, so essentially you can see there are lines of magnetism that come from one pole and loop all the way around to the other. Okay, and the Earth's magnetic field is just like a giant bar magnet, so it's just like this pretty much. So this is the basic idea. So here's the Earth, here's the Earth's magnetic field, just like a giant bar magnet. So we have the North Pole and the South Pole, and then we have these magnetic force lines that emanate from one pole, go all the way around, and then come back in at the other pole. Okay, so what we can see is two things. Number one, the strength of the Earth's magnetic field will vary ever so slightly with latitude, and the angle at which the Earth's magnetic field intersects the surface of the Earth vary slightly. So the Earth's magnetic field comes in nearly straight down at the poles, whereas it comes in a much shallower angle towards the equator. So the angle at which the Earth's magnetic field intersects the surface of the Earth changes as you move from the poles towards the equator. The angle is very steep up here and becomes very shallow down here. Okay? So this is very, very important. Why is it? Well, the most important thing is that when an iron mineral like hematite or magnetite cools down, it goes past something called the Curie point, and that will preserve the remnant magnetism of the Earth. So you're thinking, what is he going on about? All right, so if you take your index finger now and you tap it on the table in front of you, you'll hear mine. Oh, okay, that was a bad idea. The pug started barking. Anyway, let's continue. When you tap your finger on the table, you have to ask the question, why does my finger stop when it hits the table? Why doesn't my finger go through the table? It's when you think about it, it's actually a pretty obvious question. And the reason is this. As your finger heads towards the table, the electrons that make up the atoms in the tip of your finger begin to interact with the electrons in the atoms that make up the table. And because you've got the electrons are negative, you have a negative charge moving towards a negative charge, and they repel each other. So that's why the table feels solid. What's actually happening is the atoms that make up you are being repelled by the atoms that make up the table, and so it feels hard. Now, what we do when we magnetize something is we simply make the electrons orbit in the same direction. So when we expose something like a piece of metal, like a piece of steel, to a magnetic field, we magnetize it. So we make the atoms all move in just one direction, and that creates the magnetism. So the same kind of thing happens with these iron minerals. So as they're cooling down, the iron atoms in the mineral, they have electrons orbiting around them, or orbiting in them, should I say. And as the mineral cools down, it crosses the Curie point. Now, once it crosses the Curie point, the direction in which the electrons in the iron atoms orbit is set, and it's set based on the Earth's magnetic field at that time. So essentially that means the mineral will retain a signature of the Earth's magnetic field at the time that it crosses the Curie point. Now the great thing about the Curie point for a mineral like magnetite is this. The Curie point for magnetite is 580 Celsius. Now the seafloor is made up of basalt. It just so happens basalt is absolutely stuffed with magnetite. Now basalts will be solid by 900 Celsius. So the magma that forms a basalt will be 100% solidified by 900 Celsius. So that means the crystals of magnetite form by 900 Celsius, and they're locked in the rock in their current orientation, so they can never move after that point. But their ability to retain the Earth's magnetic field doesn't actually occur until the minerals cool down another 320 Celsius. So this means that the remnant magnetism, so the magnetite crystals and the remnant magnetism they retain, can never change direction because the seafloor doesn't get deformed. So essentially that means when we come along later and we measure the magnetism in these iron minerals that are in the basalt, it means we know exactly the orientation of the Earth's magnetic field at the time that that rock passed the Curie point. So we should point out the Curie point for most minerals is low, and so geologically speaking it's relatively easy to take them back up above the Curie point, and when you take them back up above the Curie point it destroys the remnant magnetic field the mineral has, and a new one will be imparted on the mineral once the temperature drops back down below the mineral's Curie point again. So you have to be very, very careful when using this kind of data. So what we do is we come along and we take a piece of the basalt, and if we know we orientate the basalt very, very carefully, and we take it back to a lab, and we orientate it once again into the position it was originally in time, in space, and we take measurements about the remnant magnetic field, and it will tell us essentially how the Earth's magnetic field was orientated at that time. So this essentially is the data that, or very similar to the data that Drummond and Matthews found when they were working for the Royal Navy. So if you look here, you can see the seafloor of the Atlantic has these stripes. It looks a bit like a barcode, doesn't it? And these stripes essentially are due to either the remnant magnetic field being either positive or negative. Okay. Now this data obviously didn't become available until after the Second World War. And what we're seeing here are changes in the Earth's magnetic field. I put a picture in that I haven't. So I'm sure you guys remember this from physical geology, but the Earth's magnetic field is not stable. It will flip. So every few million years, the North Pole will flip and will go to the South Pole, and the South Pole will flip and move to the North Pole. So when this happens, when we have one of these reversals, we get what we call a negative magnetic anomaly in seafloor rocks. When the Earth's magnetic field is orientated as it is now, we get what we refer to as a positive anomaly in the seafloor rocks. Now, because new crust is constantly being created at the spreading ridge and moving laterally away from that spreading ridge, every time the pole flips, essentially you will end up with a new orientation being imparted in the rocks, which is shown by this diagram here. Okay, so up here we have reverse magnetic polarity. That's when the North Pole flips to the South Pole and the South Pole flips to the North Pole. And then we have normal magnetic polarity. That's the situation that we have now, where the North Pole is pointing north and the South Pole is pointing south. And so what we're doing is we're taking a sequence going from 15 million years ago to the present day. Here's our spreading ridge in the middle of the ocean where new crust is being made. Okay, so the magma is rising up from the mantle underneath and forming new oceanic crust. And as new oceanic crust is formed, it pushes the old oceanic crust away from the ridge laterally. So in 50 million years ago, we have a reversed magnetic field. So that means the North Pole is pointing south and the South Pole is pointing north. So that means that signature is going to be retained by the magnetite in the rock, and that's going to give us a negative magnetic anomaly. So then, later on, the magnetic poles flip again, so north becomes north and south becomes south, at which point we're going to get a normal magnetic anomaly, as when rocks are formed at the ridge. Now 9 million years ago we get another flip, so once again north is pointing south and south is pointing north, and we get another negative magnetic anomaly. Then we have another flip here that produces this normal magnetic anomaly here, so north is north, south is south. Then 3 million years ago we have another flip that takes us back to north pointing south and south pointing north, and that creates a negative magnetic anomaly. And then takes us to the present day, where north is now pointing north, south is pointing south, and so that means the new oceanic crust and the basalts that make it up here essentially have a signature that shows a normal magnetic signature. And so that means when we look at the magnetic data, we get something like this. So imagine there's an invisible line running through the middle that essentially that corresponds to the average. Well, obviously we have some portions of the seafloor that have a negative anomaly. Those are when we have a magnetic reversal. And we have some areas of the seafloor that have a positive anomaly that refers to a normal magnetic polarity. And you'll notice, so this is where the spreading ridge is. It goes positive, negative, positive, negative, positive, negative. And we get the same repeating pattern on this side as well. And that's because the rocks are being pushed laterally away from the ridge in both directions. And so what we're seeing here is what we're also seeing here. Okay, so in black we have the negative anomaly. Sorry, I do apologize. In black we have the positive anomaly. That's when essentially the Earth's magnetic field is as it is now, and in white we have the negative anomalies. So what you're seeing is new crust is being made at the ridge, and it's slowly being pushed laterally away, and the crust essentially is retaining the remnant magnetic field of the Earth at the time that it formed. And so that's really useful because once again it shows us that new crust is being made at the ridge, and it's being pushed laterally away from that ridge as new crust forms at the ridge. And the new crust that forms at the ridge retains the Earth's magnetic signature at the time that it forms. And we can see this here. So this is off the west coast. So this is the Juan de Fuca ridge. So here we have what we've got: British Columbia up here, Washington State here, Oregon here, Northern California down here. And so what we can do is we can take the same thing and we can see the same anomalies here. So these coloured lines represent a positive magnetic anomaly. So that's when the Earth's magnetic field is normal as it is now. And the white portions represent the negative magnetic anomaly, where the Earth's magnetic field was reversed. So north was pointing south and south was pointing north. The other nice thing we can do is we can actually then take samples of the rocks and we can date them, and that can tell us when these magnetic reversals occurred. And you can actually see these magnetic reversals occur on actually a very regular basis. They're pretty common. So it shows us, number one, we have new crust being made at the ridges. That crust then spreads laterally, but also it shows us these magnetic reversals occur on relatively short timescales, geologically speaking. Okay, so that shows us that the crust is essentially being made at the ridges and moving laterally. All right, so actually I tell a lie. Let's quickly look at this diagram. So here we go. This shows you the same thing. So when we look at the age of the Earth's crust, so essentially the more red the colour, the younger the crust is. The more blue and purple the colour, the older the crust is. And what we realise is when we look at the seafloor and we find the youngest crust, we see that it's associated with these ridges that run down the middle of the ocean basins. Okay, so these ridges are clearly where new crust is being made, and as you can see, as you move laterally away from the ridge, the crust gets steadily older. Now, this is useful, but it's also useful for another reason. We can use the Earth's magnetic field to work out where a rock was on the Earth's surface when it formed. So if we just zip back to, this diagram here, as I said, the angle at which the Earth's magnetic field intersects the surface changes. So when you're towards the equator, the angle is relatively shallow, and when you're towards the poles, the angle is relatively steep. Okay, so we can actually measure that in the lab. So we can take a piece of rock from anywhere, we can take it back to the lab, we can orientate it correctly, and we can measure the angle of the Earth's magnetic field at the time that rock formed. And so what that means is we can plot where the rock was on the surface of the Earth. Essentially, the steeper the magnetic field, the closer it was to the poles. The shallower the orientation, the closer it was to the equator. And so this diagram here kind of gives you some idea. So here we have a path. This is for Eurasia, so that's Europe and Asia, and this is the path for North America. And you can see we have dates for 500, 400, 300, 200, 100, and the present day. Okay, that's a million years ago. And so what we're seeing when we look at the rocks here is we're looking at the angle at which the magnetic field intersected the surface of the Earth. So 500 million years ago, the angle was pointing upwards. So once again, if we just go back this way, here we go. So that would suggest, as the angle is pointing upwards, we're actually just south of the South Pole. No, sorry, the South Pole of the equator. I do apologise. Okay, so the angle is pointing that way. So just at the South Pole. Got to stop saying South Pole. We're just south of the equator. 400 million years ago, the Earth's magnetic field is coming in almost parallel, so almost horizontally. So that means that we're at the equator. Then steadily, 300, 200, 100, present day, you'll see the angle is steadily getting steeper, and this means we're moving towards the North Pole. So by using these changes in the angle of the Earth's magnetic field, we can work out approximately where we are. And so we can see that 500 million years ago, both North America and Europe were just south of the equator, and steadily throughout the next 500 million years, they've been travelling steadily towards the North Pole. They're moving in a northerly direction. So we can see the path that these rocks have taken. Now, the interesting thing is this. In here, that represents the Atlantic Ocean. If we subtract the Atlantic Ocean, these two lines lie almost perfectly on top of one another. So this tells us something else. This also tells us that North America, over here, and Europe from 500 million years ago to almost the present day were moving as one unit. They were moving together. They formed a continent together. And so that's another nice piece of evidence. So now I think we can agree that we definitely had these supercontinents where bits of continental crust were joined together. So the next question is how many supercontinents have we had? Now, to be clear, a supercontinent is defined as two or more pieces of continental crust joining together. So we actually have supercontinents now. We have the Americas. North America is joined to South America. We have Eurasia. Europe is joined to Asia. In fact, Eurasia is also joined to Africa as well. So we have a supercontinent there. So we actually have two supercontinents at the moment. So what are the supercontinents that we know existed? So once we start looking back through the rock record, how many supercontinents do we find? Well, we can identify 5 of them. The one you're probably most familiar with is Pangaea. That went from 300 to 175 million years ago. Then we have the 2 supercontinents that went to form Pangaea. Those were Laurasia, so that was North America, Europe and Asia. That was one supercontinent up here. And then we had Gondwana, that was another supercontinent. That was South America, Africa, Madagascar, India, Australia and Antarctica. And those 2 supercontinents existed between 510 and 300 million years ago. So 300 million years ago, Laurasia and Gondwana crash into each other to produce Pangaea. Before those 2 supercontinents, we had Pangaea. So that existed between 625 and 560 million years ago. So this is the distribution of those continents then. And this was the period of time when Africa was in contact with South America, and these bits of Cratonic crust interacted with one another and produced the Cratonic fit that we see for those 2 continents. Then we had Rodinia. That was between 1.1 billion years ago and 750 million years ago. And then we have Nuna. That was between 2 billion years ago and 1.5 billion years ago. So we believe we can pick out 5 definite supercontinents that have existed in the past 2 billion years. So the next question becomes, well, what's going to happen in the future? So this is the prediction for the future. So in the future, we predict that a subduction zone is going to open up along the eastern side of North and South America, and it's going to start subducting the oceanic crust of the Atlantic Ocean underneath it. So this means essentially Boston is going to have volcanoes in about 50 million years' time. So this is going to slowly start pulling Europe and Asia and Africa towards North America and South America. You'll notice also by this point Africa has now completely crashed into Europe, and it's formed the Mediterranean mountains. Also by this point Australia has moved north and it's banged into Papua New Guinea. And we also predict there's a good probability that Russia and Alaska will have made contact at that point. So that's 50 million years ago, 50 million years in the future. So by about 250 million years in the future, we predict that Europe and Africa and Asia have slammed into North America and South America, forming one landmass. And we also predict that the subduction zone here will pull Antarctica towards Australia, eventually leading to those two colliding, forming another supercontinent down here. And so that's what we predict will happen in about 250 million years' time. All right, I know we went a little bit over, but now it's time for a quick break. So I think you should probably take 5 minutes or so, take a really good break now because we've been going for a little while. So get up, have a walk around, have a maybe something to eat, and I'll see you in a few minutes. Okay, everybody. So I'm sure you remember from physical geology that we can work out the shape of the plates based on the locations at which earthquakes occur on the surface of the Earth. Now we're going to look at a few maps of that as part of the lab, so we're not actually going to worry about why, how we know the plates are the shape they are. We're just going to, trust the picture below down, trust the picture here, and just take it as gospel. So once we know that mid-ocean ridges are where the location of where new crust is being formed, that the trenches represent the locations where old crust is being destroyed, it becomes very obvious the surface of the Earth must be split into plates. And once you realize these plates are moving about, then obviously it becomes pretty clear that they can do one of three possible things. The plates can either bump into each other, they can move away from one another, or they can move past one another. Those are the three possible options. And so that will lead to three distinct types of plate boundary. Now before we get into them, we're just going to take a second to think about the types of crust. Now obviously, as I'm sure you remember, the Earth is made up of two types of crust. There's oceanic crust that makes up the majority of the seafloor, and there's continental crust that forms land masses and underlies very shallow seas, which we refer to as the continental margin, or the continental shelf, should I say. Now oceanic crust is pretty thin, 5 to 8 kilometers. Continental crust is a lot thicker, that's 10 to 70 kilometers. And oceanic crust is comparatively dense when compared to continental crust. So if you were to have a cubic meter of oceanic crust and a cubic meter of continental crust, the oceanic crust would weigh more. And so this means that naturally the oceanic crust, the seafloor, is going to sink into the Earth's mantle more than the continental crust will. And so that means it's going to naturally form topographic lows, and those topographic lows are going to fill with water and give us the oceans. In terms of the oceanic crust, it's made up of basalt, gabbro and peridotite. Remember, those are mantle rocks rich in olivine. And continental crust is dominated by granite, gneiss and granodiorite. So very, very felsic, lots of quartz, lots of feldspar. In the case of oceanic crust, lots of iron and magnesium minerals and quite a lot of calcium plagioclase feldspar as well. So very different compositions. So continental crust is essentially just a mess of granite and gneiss all mashed together, so I'm not going to worry about that too much. We are just going to take just a few seconds to think about oceanic crust. So oceanic crust is formed by the decompressional melting of the mantle underneath the ridge. So the peridotite underneath the ridge melts, and that produces a mafic magma. Okay? So that mafic magma is going to naturally want to rise up towards the surface. So the mafic magma will rise up and it gets stuck at the bottom of the oceanic crust, and it will begin to form a magma chamber there. Okay? Now, as that magma chamber cools, it's going to solidify to give you a coarse-grained mafic igneous rock. That's going to be your gabbro layer at the bottom. Okay? Now, about 90% of your magma will get stuck in this gabbro layer and will never make it anywhere near the surface. The remaining 10% will begin to work its way towards the seafloor. So obviously, as this remaining 10% begins to work its way towards the seafloor, well, obviously it has to push the rocks apart in order to make room for itself. So as it pushes the rocks apart, it creates a path, a fracture, along which the magma can rise. As the magma rises, obviously through that fracture, it cools and eventually solidifies, filling that fracture up. And every time it does that, it produces a dike, a vertical sheet of cooled magma. And so, directly above the gabbro, you have what's referred to as the sheeted dike complex. That's made up of these lots and lots of these sheets of typically, it's a kind of in between a basalt and a gabbro. It's a type of rock called a diabase, okay, kind of medium-sized crystals, and you get these vertical dikes one after another, and they represent essentially the crust being pushed apart to make way for the magma to rise to the surface. And then a very, very small fraction of the magma will actually make its way onto the Earth's surface, where it will be erupted in the form of basalt, and it will form a very distinct structure, which we refer to as pillowed basalts. It's a kind of very lumpy basaltic lava. So that's what we see in oceanic crust. And it's actually this portion here, the formation of the sheeted dikes, that actually causes the crust to move apart. So every time a new pulse of magma wants to make its way towards the surface, this bit of crust here needs to move that way, this bit of crust over here needs to move that way to make room for it. And so that's what pushes the old crust away from the ridge. Every time a new dike forms, it pushes the crust away in increments. So this means oceanic crust consists of the mantle peridotites, gabbros, sheeted dikes, pillowed basalts, and on top of that entire sequence you have a layer of sediment. And so that's what makes up oceanic crust. Oh, I should point out, because you have the rocks being forced apart to make room for the magma, it means you get lots and lots of very shallow, relatively weak earthquakes occurring associated with these spreading ridges. So as we discussed, once we know the plates are moving, that means we end up with three distinct types of plate boundary. We have divergent boundaries, where plates are moving away from each other, convergent boundaries, where plates are moving towards each other, and transform boundaries when plates are moving past each other. And you can see there are subgroups for each of the different types. So for divergent, we have oceanic and continental divergent boundaries. In the case of convergent, where the plates are moving towards each other, we have oceanic crust, continental crust, and continental crust collisions. And obviously transform boundaries only have one type of boundary. Alright, so what's the driving force behind plate tectonics? Well, we've said that the main force, or the initial force at least, is the circulation of the mantle driven by heat inside the Earth. So where does that heat come from? Well, the heat has two main sources. The first one is radioactive decay of radioactive isotopes within the mantle. The main isotopes are potassium-40, thorium-232, uranium-235, and uranium-238. And just like a nuclear reactor on Earth, obviously when they decay, they produce a lot of heat energy. Now the problem is the Earth's crust, or the Earth's lithosphere, should I say, acts as a duvet, and it traps that heat inside the Earth. The other source of heat inside the Earth is the heat of accretion, and that's the heat that was put into the Earth by all the impacts that actually went to form the Earth. So every time a meteorite landed on the surface of the early Earth to make it slightly larger, it obviously hit the Earth with quite a lot of energy, and some of that energy was imparted into the Earth in the form of heat energy, and some of that energy is still retained inside the Earth now. So the Earth's interior is hot because of radioactive decay and the heat of accretion. So the problem is, as I said, the lithosphere acts as a duvet, so the Earth has to get rid of the heat inside, otherwise things would run out of control. So how does it do that? Well, the first way it loses heat is at spreading ridges. So at spreading ridges, you're taking mantle rocks, you melt them, and that magma moves towards the surface where it gets erupted. So you're taking hot material from inside the Earth, transferring it to the surface of the Earth where it cools down. You're getting rid of heat, essentially. Option number two is subduction. In the case of subduction, you subduct a very old, cold piece of oceanic crust into the mantle, just like dropping ice cubes into a cup of coffee. It's going to cool the coffee down. Same thing happens here. This old cold piece of crust acts as an ice cube and helps to cool the mantle down. Then we have simple conduction of heat through the crust. So essentially the mantle heats up the bottom of the crust, and the resulting heat gets transferred through the crust to the Earth's surface, where it gets lost to the atmosphere, and then eventually gets lost to space. Conduction of heat through the crust is most efficient through the oceanic crust, simply because it's thinner. And then finally we have mantle plumes. That's when you get big balls of magma forming at the core mantle boundary. So very, very hot balls of magma. They come flying up through the mantle, and they once again get stuck beneath the crust, and that magma erupts onto the surface, once again taking hot magma, so that takes heat with it and erupts it onto the surface where it cools, and that gives us things like Hawaii and Iceland. So those are the 4 ways that the Earth can lose heat from its interior so things don't run out of control. Alright, so now we're going to look at divergent or constructive plate boundaries. That's when new crust is being made. So most constructive plate boundaries form where we have 2 mantle convection cells running parallel to each other. So they form in environments like this. So we have one mantle cell running up here like that, and one mantle cell running parallel to it like this. And this line here essentially is a path of least resistance. Okay, it's an easy path for things to move up through the mantle because they're going with the flow. So this means that if there's warm mantle down here, it naturally rises up very, very quickly and it gets stuck beneath the crust here. And once again, going back to the bed sheet and the helium balloon analogy we had earlier, it means that this area of crust here is going to naturally be pushed up by the hot mantle underneath. So that means the crust is going to start to dome. Now, once again, it's just like the plastic ruler we also discussed earlier. You can bend the plastic ruler, and the plastic ruler will bend for a while, it will flex, and then eventually you bend the plastic ruler too far, and it breaks. And that's exactly what happens. Eventually you bend the crust so far, it begins to fracture. And when it begins to fracture, magma can start making its way towards the surface, where it will be erupted. So you'll start getting volcanoes forming. So as the crust here begins to stretch, okay, because of this deformation, and fail, this portion of the crust here will naturally drop, and it will create a valley. And that valley will begin to fill up with volcanic material from the magma underneath, which is being supplied by the magma underneath. And so the valley starts to get full of very heavy, very dense volcanic material. And that also helps to pull the valley floor down, because this area here is now full of very dense volcanic material, so it now weighs more than the crust either side. So naturally that also helps to pull it down. And so as you can see, we're forming a topographic low. So that's stage 2. Now eventually what's going to happen is this area of crust here is going to become so thin that we're going to start to melt the mantle underneath it through decompressional melting. Now when that happens, that's going to cause lots and lots of mafic magma to be produced, and that mafic magma is going to rise up through the cracks in the valley floor, and it's going to start making oceanic crust. And as you start forming oceanic crust, well, that's going to start pushing both sides of the continent away from each other. So this side's going to go this way, this side's going to go this way, and it's going to be pushed. They're going to be pushed further and further away from each other as new oceanic crust is made. And then eventually you're going to get to the point where you have a fully mature spreading centre, a bit like the Atlantic, where you have a spreading ridge running down the middle, and you'll have 2 continents either side separated by a large, wide ocean, a bit like the North or South Atlantic. So those are the 4 stages of divergent plate boundary formation, and you'll actually see that the continental divergent boundaries lead to the formation of the oceanic divergent plate boundaries. So the 2 of them are intimately related. So where can we see all this happening at one time? The answer is East Africa and the Middle East. So let's look at the situation here. So in this environment we have 3 distinct zones. We have the Red Sea here, the Gulf of Aden here, and the East African Rift Valley here. Okay, and we also have another rift that's running up here, essentially between Israel and Jordan, running up into Syria and towards Turkey. And that's an area of crust that's being actively stressed right now. So what's happening is at the moment the East African Rift Valley here, this area of crust here marked in red, is currently being stretched. And it's being stretched because Somalia, or the Somali plate as it's referred to, is trying to move off into the Indian Ocean. It's trying to pull off the side of Africa. And this motion to try and rip off the Somali plate is being driven by the Gulf of Aden. So the Gulf of Aden is an area where we have new oceanic crust being made. So essentially it's a stage 3 zone here. And that's pushing the Saudi Arabian Peninsula northwards, but it's also pushing Somalia southwards. And that means it's trying to make it hinge off the side of Africa. And that's resulting in this area here becoming stretched. So as this piece of crust here tries to move this way into the Indian Ocean, it causes the crust behind it to become stretched. It gets pulled. And so that's creating this East African Rift Valley. And then over here we have the Red Sea. The Red Sea is somewhere in between stage 2 and stage 3. And so what we have is we have a situation where, and I'll show you a picture in a second, we have a large crack in the bottom of the Red Sea. And that's essentially, we are right at the point where it's almost thin enough for the mantle underneath it to start melting and for it to begin producing new oceanic crust. So when we look at it on a map, so I'm just going to show you the East African Rift Valley first of all. So this diagram up here kind of shows you the situation. So here we have the Red Sea. This is the Gulf of Aden. This is the Somali plate here. Okay, and new crust being made at the Gulf of Aden is trying to push the Somali plate into the Indian Ocean. And this means this area of crust here behind the Somali plate, and this area of crust here in the hinge region, okay, because the Somali plate is hinging somewhere around here, it's trying to be pulled. So both these areas here are currently undergoing extension. And this creates what's referred to as the Ethiopian dome and the Kenyan dome. And so you can see them here. This is the Ethiopian dome here, and this is the Kenyan dome here. And you can actually see the Rift Valley. So there it is. It's running down there. You can see it quite clearly. And this is because Somalia over here is trying to go this way away from the Indian Ocean. So this area of crust here is actively being stretched. Then we have essentially the western limb of the valley coming round here, and the eastern limb of the valley coming round here. Once again, those areas of crust are currently being stretched, and you've got a rift valley forming. And so you can actually see the Rift Valley here. This is a Google image of Kenya. So this image itself is from approximately, where was it? This region around here. Okay. And what you can see is this is the valley itself, and you can see you've got lots and lots of cracks all running approximately north-south. Okay. And those are the cracks that are being caused as this area of crust here is getting stretched. So, think of it a bit like a bit of silly putty. You're pulling the silly putty in two directions. The bit of silly putty between the two lumps in your hands gets stretched thinner and thinner and thinner until eventually it snaps. And that's what's happening here. This bit of crust is going this way. This bit of crust here is going this way. And this bit of crust in the middle is getting stretched and stretched and stretched until it eventually begins to crack. And we can see the cracks on the surface as these long linear lines. Okay, so that's the valley, and that will eventually begin to fill with volcanic material. It will get pulled lower and lower and lower by the weight of that volcanic material. It will begin to fill with water, and if the crust becomes thin enough, it will start actually forming oceanic crust, and Somalia will begin to migrate off into the Indian Ocean. So if we look at the Red Sea, what we can see is we have this linear body of water here, and we can see down the middle of it we have this rather large crack or trough, depending on how you want to describe it. So what we have here is we have a situation where a new oceanic crust isn't being made yet. Okay, but you can see the continental crust either side is being stretched to the point where the mantle underneath here is probably going to start melting sometime soon because the crust has been thinned so much. Once that starts happening, you're going to have mafic magma being produced. That's going to start making oceanic crust, and at that point it would begin to push Africa in a kind of southwesterly direction and the Arabian Peninsula in an approximately northeasterly direction. And then down here we have the Gulf of Aden. So this is a topographic map of the Gulf of Aden, and it shows you this classic zigzag pattern that you get with these mature spreading ridges. Okay, if you look at this zigzag pattern, some portions of it marked out in red, run approximately parallel to the coastline, and some portions of it marked out in yellow run approximately perpendicular to the coastline. So some portions of your spreading ridge will always run parallel to the coastline, some portions will run perpendicular. It's the portions that run parallel to the coastline, these red pieces, that's actually where new oceanic crust is being made. The yellow portions represent transform faults, and new crust is not being made there. Okay, so those were divergent plate boundaries. Now what about convergent plate boundaries? So there are three types of destructive or convergent plate boundary. There's oceanic crust, continental crust, oceanic crust, and continental crust, continental crust. And destructive plate boundaries occur when two pieces of crust bang into each other head on. So in the case of ocean-ocean and continent-ocean collisions, you will get subduction. So a piece of oceanic crust will subduct down into the mantle. In the case of continent-continent collisions, things are rather more difficult because continental crust is naturally buoyant and it doesn't want to sink. So causing continental crust to be subducted is very, very hard. So this means when continental crust runs into continental crust, neither piece will yield, and so you'll end up with a very, very big mountain range like the Himalayas. So the friction of these pieces of plate banging into each other and moving past each other will produce numerous, very, very large earthquakes. It will produce lots of volcanic activity in the case of ocean-ocean and ocean-continent collisions. And they will also, in some cases, in the case of ocean-ocean and continent-ocean collisions, produce tsunamis. Alright, so let's start off with the most straightforward version first. Continent-continent collisions. So continent-continent collisions when you have two pieces of continental crust bang into each other, and of course neither piece of continental crust will want to subduct, so all they can do is just run head-on into each other, producing a very large mountain range. So the classic example of that is India. At the moment, India is moving northwards. Approximately 40 to 50 million years ago, it started crashing into Asia, and that resulted in the formation of the Himalayan mountains. Now, what tends to happen is one of the pieces of continental crust, when they bang into each other, one of them will be ever so slightly what we refer to as underthrust. So in this diagram here, imagine this is India. India is being ever so slightly underthrust underneath Asia. And obviously you have the old oceanic crust that separated them is being subducted down and lost into the mantle. Now the key point is this: because nothing is subducting and melting, that means no volcanoes. So continent-continent collisions do not have volcanoes. They do, however, have lots and lots of earthquakes because you have two very, very large pieces of crust banging into each other, which stresses the rocks, so you get lots of earthquakes. So what happens in the case of ocean-continent collisions? So in the case of ocean-continent collisions, the oceanic crust, which is cold and dense compared to the continental crust, which is more warm and buoyant, well, the oceanic crust will subduct underneath the continental crust. And so obviously you'll have this area where the two pieces of crust are in contact with one another, and that's going to be an area that produces lots and lots of tectonic forces. And that's going to result in the crust being buckled, it's going to fold, and it's going to cause large pieces of rock to be thrust, to be pushed one on top of another. So here we go, this is a diagram here that shows the process. This is thrusting, so this sheet of rock here, you can see it there, is being pushed over this sheet of rock down here, along a thrust fault, a low angle fault. Then another piece of rock here gets pushed over the top of this piece of rock. So you end up with one layer of rock coming over the top of another layer of rock. Then another layer of rock comes over the top, and so on and so on and so on. And so each one of these pieces of rock builds up what's called a thrust sheet, and the total thing is called a thrust duplex. And if you notice, every time a new layer of rock gets pushed up, well, what's happening? The mound here is going to get higher and higher and higher and higher. And you're going to get a mountain range. So mountain ranges are the result of folding of rocks and buckling, but it's also the result of pushing one sheet of rock on top of another, on top of another, on top of another to build up a topographic high. So you can kind of see it here. So these are two pictures from mountain range. You can kind of see the buckling of the crust, the folding. That's very, very common. And so what's happening here is you're taking a sheet of rock that's only that thin from there to there, and essentially you're making it from there to there. You're increasing the thickness by folding it. So you're making the layer of rock much, much thicker. Okay. The next thing is you can see from this picture here, you can see we have these thrust sheets, these sheets of rock that are being pushed one on top of another. So you can see this sheet of rock here is being pushed over this sheet of rock. This sheet of rock here is being pushed over this sheet of rock, and this sheet of rock here is being pushed over this sheet of rock. So you've got one layer on top of another on top of another, and these layers going over the top of each other produce mountains. And so that's where a mountain comes from. And you can see it here. So this is a geologic cross-section from the Calgary area in Canada. Okay. Now the mountain range that's here formed a very, very long time ago, so it's been eroded away, so the land itself is very flat. But once again, we can see the signatures of the mountain range having been there, especially in this picture down here. We can see we have one layer of rock going over another layer of rock. We have another layer of rock going over this one. This layer of rock goes over, these layers of rock, go over these layers of rock, and these layers of rock go over these layers of rock, and then these layers of rock are going over these layers of rock. So essentially that would have been one layer on top of another layer, another layer, another layer, another layer, and you would have had a topographic high, which you would see as a mountain. So these thrust duplexes are very, very important when it comes to mountain building. And they're the result of the collision between two large pieces of crust. So we get them at ocean-continent and continent-continent collisions. And it's an important point to note that these thrust duplexes form on the continental crust only. That's why we don't see them forming at ocean-ocean collisions. So we have these thrust duplexes and these folds that make these big mountains, and then we have additional mass being added from big intrusions, from magma that enters the mountain range where it cools and solidifies, which makes the mountain, which helps to add bulk to the mountain range. So in terms of the oceanic crust contains significant quantities of water in its minerals, and also in pore spaces and in cracks in the rock. So as the oceanic crust plunges down into the mantle, the rock begins to get heated up. Now, at approximately 100 to 150 kilometers down, the subducting piece of oceanic crust suddenly loses water from its minerals. It's called dehydration. So the minerals lose water. Now that water has to go somewhere. So where it goes is into the surrounding mantle rock. Now, mantle rocks and water do not play well together, and so when you add water to a mantle rock, it causes the mantle rock to start melting. And so that's going to produce hydration melting, and that's going to produce a mafic magma. Now that mafic magma is going to be buoyant, and it's going to want to rise, and so it's going to rise up, and it's going to get stuck at the bottom of the continental or oceanic crust. And when it gets stuck there, it's going to start melting the continental or oceanic crust through the process of thermal melting. So you need to remember, so a mafic magma, for instance, has a temperature anywhere between 950 and 1200 Celsius, whereas continental crust will start melting at 700 to 800 Celsius. So when you put a big ball of mafic magma in contact with continental crust, it's going to start melting, and when the continental crust starts to melt, it's going to produce intermediate and felsic magma. Okay, so the types of volcanoes we see at continent-ocean and ocean-ocean collision zones are not basaltic volcanoes, they are felsic to intermediate volcanoes. And that's because the magma that's feeding those volcanoes is not forming from the melting of the mantle, it's forming from the melting of the continental or oceanic crust. And that crust is being heated up by the magma that formed due to the melting of the mantle. So that's a key point that you need to keep in mind. So here's our basic situation. Here's our piece of oceanic crust. This is a continent-ocean collision. Oceanic crust here in blue, continental crust here in brown. So our piece of oceanic crust plunges down to about 100 to 150 kilometers. At that point, the minerals in the crust lose water. That water goes into the overlying mantle. The mantle becomes unstable. It begins to melt, producing a basaltic magma. That basaltic magma rises up, gets stuck at the bottom of the continental crust. It begins to heat up the continental crust. The continental crust then starts to melt, and that magma then rises up through the continental crust and feeds volcanoes in the mountain range. It just so happens that the continental crust will produce felsic and intermediate magmas, and these magmas are very, very rich in water and other dissolved gases, and so that means the volcanoes within continent-ocean and ocean-ocean collision zones are very prone to exploding. Think Mount St. Helens. So we also have data because we can track the path taken by this piece of subducting crust, because we can look at the earthquakes that it causes as it goes deeper and deeper into the earth. And we can see from the earthquake data that some pieces of subducting oceanic crust make it nearly all the way down to the core mantle boundary. So subduction goes very, very deep in the earth. So these very, very deep earthquakes that we detect can be related to this slab, this subducting piece of oceanic crust just simply breaking up, like flexing a ruler too much. Or it can be due to very, very violent changes in mineralogy caused by metamorphism. So as the minerals change, it causes the volume of this piece of crust to change, and that causes essentially very, very violent changes in the size of the crust, and so that can lead to earthquakes. Now in the case of ocean-ocean, it's very, very similar to ocean-continent. So we have a piece of oceanic crust here that subducts down, it melts, producing magma. That magma rises up, gets stuck at the base of the crust, starts melting the crust, and the resulting magma then rises to the surface to feed volcanoes. So exactly the same mechanism. Now in the case of ocean-ocean, you're probably thinking, well, hold on a minute, this piece of rock here is an oceanic crust, this bit over here is oceanic crust. So why does this piece subduct but not this piece? And the answer is quite straightforward. This piece of oceanic crust is attached to a piece of continental crust. And the continental crust kind of acts like a life preserver. So it gives this piece of oceanic crust buoyancy. So it makes it less likely that it will sink. And so this is what's happening with Japan. So Japan's sitting on a piece of oceanic crust, whereas the Pacific plate here subducts underneath Japan. Japan does not subduct underneath the Pacific plate because this piece of oceanic crust here on which Japan sits is stuck onto the side of Asia. So Asia essentially is adding buoyancy to this piece of oceanic crust here, meaning that it cannot subduct. So when the Pacific plate hits this edge here, it means the Pacific plate will subduct down into the mantle. Now, the resulting chains of volcanoes that form have a very, very distinctive curved morphology to them, and that's why they're often referred to as island arcs. And so here we go, this is the Pacific itself. So you can see here's the trench that we get in front of these subduction zones. So wherever we have a ocean continent or ocean-ocean subduction zone, we will have one of these trenches. So this is ocean-ocean here. And you can see this area of oceanic crust here is attached to Asia and North America, and therefore it's more buoyant than the Pacific plate here, which is not attached to continental crust, and so the Pacific plate will subduct underneath this piece of oceanic crust here. So that's an ocean-ocean collision. Okay, and you can see the chain of volcanoes there, this island arc, those are the Aleutian Island volcanoes. Now over here we have a trench that's related to the Cascade volcanoes, so that's Mount Baker, Mount Rainier, Mount St. Helens, and that's when this piece of oceanic crust here, the Juan de Fuca plate, you can kind of see the edge of it coming down there. The Juan de Fuca plate is subducting underneath North America, producing the Cascade volcanoes. There's a weak trench there. It's not easy to see, I'm going to be honest. And in this case, we have a whole load of mountains being formed by that collision. Okay, and so that's the Cascade range of mountains. Now, the volcanoes in this case don't form an arc. They just form a line parallel to the coastline. But in both cases, ocean-ocean and ocean-continent, we do form a trench in front of the volcanoes. So then we have another island arc here, another island arc there, another island arc there, another island arc associated with the Philippines, and then we have some more island arcs as we come down here towards Papua New Guinea. You can see another little one here. Okay, so we have another one here that separates Japan from Taiwan. Okay, so you can see that we have lots and lots of these island arcs associated with these trenches in the seafloor. We should also, of course, remember, as we discussed earlier, there are these chains of linear volcanic islands, and those are related to hotspots. So that's the Hawaiian chain and the Empress Seamount chain. So the angle of subduction dictates where a volcano will form. So the shallower the angle of subduction, the further back from the trench the volcanoes will form. The steeper the angle of subduction, the closer to the trench the volcano will form. So here's our subducting piece of oceanic crust, here's our piece of continental crust, and here's the trench that sits in front of the, essentially sits at the subduction zone, and that marks where the oceanic crust is subducting down into the mantle. So how does it actually affect what's going on? So here we go. So this is an image of the Wegener plate. So that's oceanic crust, which is this bit of crust here, subducting under North America. So this is Mount Rainier right here, this little red triangle. Okay, North American, so continental crust, Pacific oceanic crust. And what we've got here is we have a map that's been produced by geophysicists, and it shows us where the pieces of crust are going. So there is the piece of oceanic crust, the Wegener crust, subducting underneath North America. So it's subducting down underneath North America, and it's reaching the magic 100 to, in this case, 120 kilometer range, so somewhere down here, and it's starting to melt. And we can see the melting occurring as these red and orange colors here. This is where the magma is being formed. And so this magma starts rising up towards the surface, and it feeds volcanoes on the surface like Mount Rainier. Okay, so essentially the shallower the angle, well, essentially in this case the angle's not too steep, but the angle of subduction is reflected by the position of the volcano. So as soon as the plate hits this magic 100 kilometer to 150 kilometer depth, it starts to melt, and it produces magma that rises straight up and feeds volcanoes at the surface. Now, let's just say, for argument's sake, that the angle of subduction is slightly different. Maybe it's even shallower. So the Wegener plate takes even longer to make it to the magic 100 to 150 kilometer depth. So that means it takes a lot longer to melt, and so that means the volcanoes that form are going to be a lot further away from the trench. So the shallower the angle of subduction, the further back from the trench the volcanoes will be. So what's actually controlling convergent and divergent plate boundaries? Well, we've already discussed that quite a lot of what's driving the force is mantle convection. So I'm actually going to skip back quite a few slides now, just for a second. Back to a diagram. Where are we? There we go. So what you'll notice is where we have these spreading ridges, that's where mantle convection cells are coming up, and we have subduction where mantle convection cells are going down. So clearly mantle convection has a very important part to play when it comes to plate tectonics. However, mantle convection is kind of the starting force. Okay, so it's kind of the starter motor. Once the process actually gets going, two other forces actually kick in that are more important, and these forces are ridge push and slab pull. So in the case of ridge push, essentially it's a pushing force that pushes the crust away from the ridge as new crust is made. So as new crust is made at the ridge, older crust gets pushed laterally away. So that's the first force, ridge push. So then we also have slab pull. And slab pull is the result of the piece of oceanic crust descending down into the mantle. Now the weight of the piece of oceanic crust subducting down into the mantle obviously gets pulled down under gravity. And as it gets pulled down, it pulls all the oceanic crust behind it down with it. And so the two forces that really control plate tectonics are ridge push and slab pull, with a minor input from mantle convection. When it really comes down to it, 90%, give or take a little bit, of tectonic forces is the result of slab pull. Gravity is the all-important force, and so gravity pulling down this piece of oceanic crust, pulling all of this material along with it. Essentially, that's what helps to drive most plate tectonics. And then finally, we have transform or conservative plate boundaries. Do you know what? We're just going to take a very quick break. We're ever so nearly there. Just get up, have a quick walk around, take a minute, and then come back. We've only got a few slides to go. Okay, so the final plate boundary are the transform or conservative plate boundaries. Now that's where pieces of crust simply move past one another. So nothing's really getting made, nothing's getting destroyed. Now, because pieces of crust are moving past one another, nothing is melting, so there are no volcanoes. However, once again, because we have two pieces of crust grinding against each other, there are going to be lots and lots of earthquakes. And in fact, transform plate boundaries are quite dangerous if they're on land, because they tend to produce lots of very big earthquakes that are relatively shallow. Just ask anyone that lives near the San Andreas Fault. So why do transform boundaries actually exist? This diagram up here sums it up quite nicely. So here we have plate A, and on plate A we're going to have a divergent plate boundary open up here, so new crust is going to be made on this side, and that means obviously old crust has to be destroyed over here at a convergent plate boundary. And so plate A obviously starts moving this way. Now this means that obviously along the edges here you have a situation where crust is not being made or destroyed, but plate A has to slide past plate B and plate C, and so obviously along here and along here we have to have transform plate boundaries, otherwise this sliding motion could not occur. And transform plate boundaries can be seen, so this is the San Andreas Fault here, and you can see this is the fault itself coming along here. These hills, these gentle hills either side, that's a result of bits of broken up rock produced by the grinding of the two pieces of crust moving past one another. So in the case of the San Andreas Fault, the western side here is moving northwards towards Alaska, and the eastern side here is, comparatively speaking, moving southwards towards the equator. Okay, not really that much. It's mostly this western side here is moving north. And so California is slowly but surely, should I say the western side of California is slowly but surely moving up the west coast. So eventually it's going to go past Oregon, past Washington State, past British Columbia, and eventually if it continued all the way up, it would end up becoming part of Alaska. So yeah, so without transform plate boundaries, plate tectonics just wouldn't function. Okay, and we can see it here. So this is the Pacific. So we can see the Pacific plate is trying to move off to the northwest, so it's heading up in this direction. New crust is being made down here, which is providing the new material to move off to the northwest. And so that means obviously when the Pacific plate is moving past the North American plate here, well obviously you can't have crust being subducted, you can't have crust being made, so the piece of Pacific crust just simply has to move past the piece of North American crust. And we can see the same thing happening here. So this is the Mid-Atlantic Ridge. Once again, we can see the step, so that instantly tells us this is a divergent plate boundary where new crust is being made. And we know that wherever the boundary is essentially facing the continental crust, we know that's where new material is being made. So these red lines here represent where new oceanic crust is forming. And these yellow lines here represent the transform faults that are in between them. So if I just go back for a second, we can see it in this diagram here. So this is where new crust is being made, these ridges here, and these transform boundaries link these sections of the ridges. And that's simply because mid-ocean ridges do not produce oceanic crust at the same rate everywhere. Some portions of it will create oceanic crust faster, and some portions will create oceanic crust more slowly. And so essentially the sections that produce crust at different rates will begin to move away from one another, and the only way they can do that is by having these transform faults, and that produces this very, very distinct stepped appearance that we see at these divergent plate boundaries. So this table here just summarizes what we've been discussing. I'm not really going to go into it now, you can read it yourself. So the final point is this: what happens if we don't get rid of the heat inside the Earth? So when it really comes down to it, plate tectonics is just a mechanism to keep the Earth's interior cool. So what happens if what would happen if we didn't have plate tectonics? Excuse me. So the process that would happen is called catastrophic resurfacing. But what does it actually mean? Okay, so at the bottom here we actually have a picture of Venus. So in the 1970s and 1980s, the Americans and the Russians sent quite a few satellites to Venus trying to look at the surface. And the images they sent back look like this. So essentially the blue-purple areas are the lowlands, and the kind of pinky areas are the highlands. And the one thing they noticed was that Venus had a distinct lack of impact craters. So compare Venus to Mars, or Vesta, which is a very large meteorite in the asteroid belt. You can quite clearly see both Mars and Vesta are just absolutely covered in impact craters. Go back to the picture of Venus. there's practically none there at all. Now, Earth also has very few impact craters, but Earth has plate tectonics, so some impact craters in the oceans would have been subduction and lost. And we also have erosion because we have liquid water. So that means impact craters on the continents will get filled in, and once again, we'll lose them. We won't be able to see them. Now, in the case of Venus, there is no plate tectonics and there is no erosion. So the question becomes, where are all the impact craters? And when we look at the crust of Venus, well, something has clearly gotten rid of all those impact craters. So when we date the crust of Venus, we see the crust of Venus only dates to about 500 million years old. So geologically speaking, it's very, very young. So why does Venus have such a young crust? Well, the answer is it just doesn't have plate tectonics, so it doesn't get to lose that internal heat from its mantle. So that means its mantle is getting hotter and hotter and hotter. You also need to remember that Venus is approximately the same size as Earth. So it has this, essentially the same internal structure as Earth does, has the same amount of radioactive isotopes, has the same amount of heat from accretion. But in the case of Venus, it can't lose some of that heat through plate tectonics, so its mantle is getting hotter and hotter and hotter and hotter and hotter until eventually it reaches the point where the crust begins to melt. Now obviously the crust begins to melt so that some of the heat from the mantle can escape. Obviously, once the crust melts, though, well, should I say all or the vast majority of the crust will melt, and that will mean, obviously, any features on the surface of Venus, like meteorite craters, will be lost because the crust therein will be destroyed. So, if we didn't have plate tectonics, every few 100 million years, the surface of the Earth would literally become liquid, and, we would be in a lot of trouble. But luckily, we have plate tectonics, and so that's not a problem for us. Okay. So that's the end of the lecture. I appreciate it was a long one, but well done for making it through. So please don't forget the code word at the start of the lecture. Right, I will see you during the lab class. Take care.